Last time we discussed operational amplifier feedback in op-amp using the inverting and non-inverting configuration. And then we explored circuits such as the difference amplifier, integrator, differentiator, and precision rectifier. Today we'll revisit some of those op-amp configurations from last time, as well as we look at some of the circuits in more detail, like the precision rectifier, log amplifier, and Schmitt trigger. So the basic op-amp is a 3-terminal device. The way the symbol is drawn, it has 2 inputs, 1 and 2, and the output at the terminal 3. The ideal characteristics of an operational amplifier are that it has infinite input impedance, which means no current can flow into these terminals 1 and 2. It has 0 output impedance at the terminal 3, and it basically functions as a comparator. That means the output at terminal 3, so V out, is equal to some gain value A times V2 minus V1, where V2 and V1 are the voltages applied at terminal 2 and 1 respectively. The reason I've written 2 minus 1 is because of the way these terminals are labeled with a plus sign and a minus sign. So whatever voltage is applied to the terminal with a plus sign and a certain voltage which is applied to the terminal with the minus sign, they subtract out in this form. So the output voltage is the difference of the 2 inputs. Now, a comparator is basically a device which compares 2 inputs. It tells you which one is higher or not. So if you look at the op-amp characteristic, it says that the third point was it has 0 common mode gain or infinite or equivalently infinite common mode rejection. That means if V1 and V2 are equal, then the output will be 0. So there is 0 common mode gain. When there are common inputs, the op-amp also in point number 4 has infinite open loop gain, which means the value of A is very large. It's supposed to be infinite. That means even if you have a very tiny difference between V2 minus V1, you will get a clear signal of it at the output. And then infinite bandwidth, which has got to do with the frequency of signals. We'll not look at it now. So how does a basic comparator work? If V2 is greater than V1, if V2 is greater than V1, then that implies V out is positive. And if V2 is less than V1, that implies V out is negative, right? Now, when you say that the op-amp has infinite open loop gain, so what does open loop mean? There is no loop in this figure. When we come to closed loop, you'll understand what is open loop. So right now, this figure is an open loop system because there is no connection from the output to the input. If it has a gain of like, this is a practical number. So if it has a gain of like 2 lakhs, that is like 2 into 10 to the power 5. Then let's say at the input, let me write this correctly, power 5. So if it has a gain of 2 into 10 to the power 5, then for a small change in the input, let's say that, V2 minus V1 is equal to 1 microvolt. Then what is the output going to be? V out is going to be 2 into 10 to the 5 times 1 into 10 to the minus 6. So that's 0.2 volts. So even for a 1 microvolt difference, you can get like a 0.2 volt at the output. So if the input difference is 1 volt, so let's call this as delta V is V2 minus V1. So if delta V were 1 volt, then what will the output be? It's going to be 2 lakh volts. 2 into 10 to the power. And clearly this device is not going to be able to generate 2 lakh volts. So where is this energy coming from at the output? We say the output is some gain times the difference of inputs. So where is this gain coming from? That means there is some power supply in the system, which is over here. Okay. So every op-amp has a power supply, which is given by VCC and minus VEE, just like the BJT terminals. So the system at the output can never generate more power than what is supplied to it. So when we say that the delta V is 1 volt, the output can never reach 2 lakh volts. It will saturate at the value of VCC. So the maximum value of the output is VCC. So V out max is equal to VCC. What is the V out minimum? It's going to be minus VEE. Okay. So the output voltage goes between VCC and minus VEE, and that is what is shown in this figure. So the x-axis is the input voltage VI. VI is equal to what? V1, V2 minus V1. VI is V2 minus V1. That's what is being plotted on the x-axis. So if VI is a large number, so if VI is somewhere over here, then the output V out will become 8 times the value of VI. And if A is like about 2 lakhs, which is a very large number, then the output saturates at VCC. So the V out is given over here. V out is equal to A into V2 minus V1. So when V2 minus V1 is a larger number, then the output saturates at VCC. Similarly, if V1 is greater than V2 and it's a negative number, the output saturates to minus VEE. Okay. And in between, if you have like a small value, supposing you have the V2 minus V1 is like 1 microvolt, then the output is like 0.2 volts. So that is like somewhere along this line. So this line may be like going from, say, these ranges on the x-axis might be like, say, from minus 10 microvolts to 10 microvolts. So any number which is greater than 10 microvolts, for example, okay, 10 microvolts is not a, it's a number I took at the top of my head. What I'm trying to show is if there's a very tiny change in the input, then the output will follow a slope which is given by A, because that means the output is A times V2 minus V1. If the change in the inputs is much larger than this, then the output will saturate, because you cannot get a very large output. It will saturate to what the power supply is giving. So this is the basic working of the ideal op amp. Now, if you want to, try to come up with new, functionalities with op amp, then there are various ways to do it. So the first thing is you have to go to a closed loop system. That means the output is now connected to the input terminal. Okay, so that is a closed loop system. Earlier it was an open loop system. That means there is no connection between the output and the input. So let's see what's the advantage of using a closed loop system. Now there are two kinds of feedbacks over here. So when you're supplying the output back to the input side, it's called a feedback, and we saw feedback in BJT as well. So here this system is called a negative feedback because the output is connected to the negative terminal. That means whatever output is coming is being fed back negatively to the input. So the difference, because we said that the input side is basically V2 minus V1, and the output is some gain times V2 minus V1. So now if the output is the amplified difference of the inputs and that is fed back to the negative terminal, so this negative value is increasing. Okay, so that way you are getting a negative feedback into the system. So let me just get this out of here. So first of all, the point you have to notice, when the output is connected to the negative terminal, this is called negative feedback. Then there is something called inverted configuration within the negative feedback. So inverted configuration means the input is supplied to the negative terminal and the positive terminal is placed at ground. Okay, so this is called the inverted configuration. Similarly, you have something called the non-inverted configuration. Here the input is given to the positive terminal and the negative terminal is connected to ground. But remember, both of these are negative feedback because the output connecting to the negative terminal is the negative feedback. In this case also output is connecting to the negative terminal. This is negative feedback. Then there is inverted configuration, which means the input is given to the negative terminal, and there is non-inverted configuration, which means the input is given to the positive terminal. So it's a combination of the input and the outputs. Now, once you have the concept of negative feedback, then there are some golden rules of the op amp for negative feedback, which means the output attempts to do whatever is necessary to make the voltage difference between the inputs zero. So in the earlier case with the comparator, we saw that if you have some difference between the inputs, if V2 is greater than V1, the output will go to a positive number and saturate over there. If V2 is less than V1, then the output will go to some negative number and saturate over there. But in this case, in this open loop case, V1 and V2 are unaffected. They're fixed. I'm giving say 1 volt here and 2 volts here. It always stays as 2 volt and 1 volt. Whereas in the case of negative feedback, you have given your input, but now the output which is generated is being fed back to the input and it's cancelling off a part of the input. So now actually what's happening is every time the output is generated, it is affecting the input further. So this is the feedback system. And as a consequence, this statement says that the output will attempt to do whatever it can to ensure that terminals 1 and 2 reach the same voltage finally. Okay. And then the second point is the input draws no current. We already know this because there is infinite input impedance to the op-amp. How it's infinite, we don't know. We are accepting it. So the op-amp is a system which has infinite input impedance. So no current will flow into the system. And the output will do whatever is possible so that the two inputs will float to the same potential value. Now, if we accept this, then basically there is something called the concept of virtual